Welcome to This Explainer. Today, we're diving into the fascinating and, honestly, sometimes terrifying world of industrial machinery. We're going to diagnose how tiny, almost invisible flaws in hydraulic systems can lead to massive mechanical failures. But more importantly, we'll look at how modern engineering is fighting back with some absolutely incredible tech.
So let's start with a really high-stakes question. What exactly causes the catastrophic cylinder drift that jeopardizes rotary wing aircraft stability systems or heavy shipping equipment? You know, it's pretty wild to think that a multi-ton crane or a helicopter's stability control can be completely compromised by a single microscopic scratch. But that is exactly what happens when hydraulic integrity starts to fail.
All right, here's our roadmap for today's investigation. We'll cover the threat of cylinder drift, root causes and parameters, detecting the invisible leaks, predicting failure with AI, and finally, smart control and prevention.
Okay, Section 1. The threat of cylinder drift, symptoms of a failing machine.
To really wrap our heads around this, let's think of the machine as a patient. We're looking for the very first symptoms it shows when something goes wrong internally. Cylinder drift basically happens when there's unintended movement or a subtle loss of pressure inside the hydraulic system. Just picture an excavator boom slowly drooping under its own weight, or a helicopter's flight controls just not responding crisply. These symptoms cause massive downtime, they tank efficiency, and, crucially, they introduce severe safety risks. When fluid leaks past the seals where it definitely shouldn't, the machine essentially loses its holding power and its control authority.
Moving on to Section 2, root causes and parameters, the underlying disease.
Think of the hydraulic fluid as the machine's blood, and the main electric pump as its heart. The pathways mapped out here are exactly where our patient can suffer internal bleeding, or in engineering terms, internal leakage. So the pump draws fluid from the tank, pushes it through the directional control valves, and straight into the linear actuator. Any scratch, wear, or damage along these high-pressure pathways alters the pressure differential, and that causes fluid to bypass the piston seals, creating that really dangerous drift we just talked about.
These are the specific physical parameters, the organs of the system, if you will, where friction, internal leakage, and seal wear most commonly originate. The linear actuator seals wear down from abrasive particles. The proportional directional control valves, they suffer from wear that causes cross-port leakage. That means fluid is essentially slipping between chambers where it absolutely shouldn't be. Even the main pump's internal clearances can just open up over time. And keep in mind, all of these components are constantly subjected to dynamic loading, which just accelerates their degradation.
Section 3. Detecting the invisible leaks, running diagnostics.
So, how do we catch this? Well, we have to contrast the old era with the new. Traditionally, industries relied on time-based maintenance, or TBM. It's kind of like servicing a machine completely blind, just sticking to a rigid schedule. Massive transport ships might miss their scheduled service entirely because they're deployed at sea. Or, on the flip side, parts get over-serviced when there's actually nothing wrong with them. Today, we're shifting to predictive maintenance, or PDM. This means treating the machine based on its real-time vitals, allowing engineers to intervene the exact moment degradation begins.
Through run-to-failure tests on dedicated hydraulic test rigs, researchers have actually mapped out this physical degradation timeline. It goes from a perfectly unworn seal to a piston rod that gets a tiny, tiny longitudinal scratch from hard debris. Now, that single scratch acts like a cheese grater. It accelerates the seal wear with every single stroke until it finally leads to detectable fluid leakage. The whole objective of modern diagnostics is to catch this at step 2 or 3, well before we ever hit step 4.
Which brings us to Section 4, predicting failure with AI, listening to the vitals.
Enter the ARIMA model. This is an absolutely brilliant diagnostic tool. ARIMA is an autoregressive pattern recognition engine that can literally hear microscopic scratches using acoustic emissions. We're talking about sensors that pick up high-frequency stress waves, somewhere between 0.5 and 2.5 megahertz. These waves are generated by fluid squeezing through a damaged seal, long before a human operator notices anything feels off or a puddle forms on the floor.
What's truly fascinating is how we can track these acoustic signals over time. By extracting mathematical features like root mean square from the acoustic data, we can literally watch the wear progress. As the seal degrades, the acoustic energy goes up. By feeding this data into the ARIMA model, engineers can forecast leaks with prediction errors as low as 4.95%.
But let's be real. Outfitting every single machine with acoustic sensors can get incredibly expensive. So as a cost-effective alternative, researchers have found a way to run diagnostics without adding any new sensors at all. They extract features straight from the existing control signals that are already driving the valves. When internal leakage happens, it alters the system dynamics, forcing the controller to work differently just to maintain its position. Now, this sensorless detection is perfect for machines with consistent loads, like a hydraulic press. However, it's a lot more challenging for stochastic, unpredictable loads like an excavator, where random external forces can actually mimic the signal changes of a real leak.
Section 5. Smart Control and Prevention. The Cure. So what is the cure? We use digital twins. By utilizing RX models, which stands for autoregressive with exogenous inputs, basically meaning it accounts for external forces, engineers can create a virtual replica of the hydraulic system. It's a good enough mathematical twin that perfectly balances computational efficiency with actual diagnostic capability. It runs on edge computing platforms right there on the machine, constantly comparing the real actuator's behavior against the virtual twin's perfect behavior. This allows it to pinpoint exactly which valve or seal is failing, conducting root cause analysis right on the fly. And the profile we are looking at here brilliantly illustrates the intense dynamic load and position demands these systems face in the real world. To prevent cylinder drift under these wild cyclic loading conditions, engineers are now embedding dynamic models directly into the control loop. Instead of just blindly reacting to a pressure drop, a modern dynamic controller actively calculates inertia, friction, and leakage in real time. It instantly compensates for any nonlinear changes before the load can even start to drift.
So the crucial point here is this incredible number. By embedding these dynamic mathematical models, this new smart controller architecture achieves a massive 98.3% fault detection accuracy. It can automatically classify pump faults, pressure valve failures, and flow control anomalies with shocking reliability. Furthermore, when applying this active compensation, the controller achieves an incredibly precise maximum trajectory tracking error of just 0.28 millimeters. Let that sink in. That means even if a cylinder is internally bleeding pressure under rapid load changes, the smart controller corrects for it so fast that the machine's actual movement deviates by less than 1/3 of a millimeter. It's essentially masking the disease while simultaneously alerting the surgeon.
It is truly amazing what modern engineering can pull off. I'll leave you with this final thought to ponder about the incredible future of predictive maintenance. If we can now hear a microscopic scratch using acoustic emissions, predict a leak with AI before it drops the pressure, and correct for it in milliseconds using dynamic digital twins, will unexpected machine downtime soon be a thing of the past? Thank you for joining me on this explainer. I really hope this gave you a brand new perspective on the invisible, high-stakes battle happening inside heavy machinery.